Okay, so let me share. 1 second, I'll just check whether. Okay, okay. So, okay, so welcome to this ninth class on electromagnetic theory. And I'm Sadhvi. I'm doing this as a part of the PMRF ship. And in the last few classes, we started from electrostatics and then, you know, gradually built upon it. And then we moved to magnetostatics and then we went towards time varying situations. So gradually we got to see how electric and magnetic fields can be correlated to each other. And that's the reason why we are studying electromagnetism as a single subject. And then, so there came the equations. Then we moved towards studying electromagnetic waves, okay, how light is an electromagnetic wave and all of that. And in the last class, what we had done is we saw that based on the frequency or wavelength of our signal and how comparable the dimensions of our connecting wires or transmission lines are, in many cases, what can happen is this connecting leads can alter or affect the signal that is getting transmitted. So when that happens, we are no longer in the lumped circuit regime, but we are in a distributed circuit regime where now we have to take into account the effect of this transmission lines. And there we discussed about this different distributed parameters where we described the effect of the transmission line in terms of R, L, C, and G. Okay. And we defined them per unit length of the transmission to small lumped circuits. Okay. And for each section, we had this different distributed parameters. And then we built upon that to see that suppose if you have some, you know, load at some point, what will be the, impedance at the source or vice versa. So all those kind of questions we wanted and we did discuss in the last class. And there what we saw is that when this transmission happens, there can be a phase that can come in, new phases, which depends on the distance traveled. Okay, so new phase can come in, or depending on what the properties are, you can also have loss in the signal where your, there can be attenuation where the amplitude drops exponentially as you proceed as the transmission happens. So all those kind of different changes can come up in the signal due to transmission lines, and we discussed about how to quantify that. Okay, so what we will do today is basically we'll build upon this very idea of transmission line, but now we will look at a very like easier graphical method of evaluating or calculating this kind of uh, you know impedances or reactances so that we can have our desired conditions. So suppose if we want impedance matched circuits, we want maximum power transfer, or we want a certain SWR. Okay, so if we want to design circuits with these requirements, then we need to know what our load impedance should be, or how can we match the impedance and all that, right? So all these can be evaluated quite easily in a much simpler graphical method, and that's the Smith chart method, and that's what we'll be discussing today. Okay, so this is basically the Smith chart is basically a graphical plot of normalized resistance and reactance. Okay, in reflection coefficient plane. Right. So what does this mean? So first is when we say normalized reactance or resistance, with respect to what are we normalizing? So we are normalizing it with respect to the characteristic impedance of our transmission line. So you remember when we had in the last class we discussed that you can define like based on this RL, G and C values of your transmission line, like the distributed parameters, you can define a characteristic impedance of your transmission line, right? And we saw that if your input impedance matches with the characteristic impedance at the source end, and then at the load end, if the load impedance matches with the characteristic impedance, then that's the impedance matched condition, right? So here what is being said is this is a graphical plot where all the resistances and reactances will be normalized to the characteristic impedance of your transmission line. Okay. And then uh, they'll be plotted in the reflection coefficient plane. So if you remember, we saw that if there is some difference in impedance, then there'll be some reflected wave, right? And the reflection coefficient determines how much of the wave will get reflected, right? So this was a typical relation which related the load impedance and the characteristic impedance, and this ratio of this like this relation was defined as the reflection coefficient. It gives us, so if you know the reflection coefficient, you know that if you have some incident voltage at the source end, and then when it gets reflected from the load, how much will be the reflected voltage. So that comes from this reflection coefficient, right? So now you can understand that if your is now a complex quantity, okay, so if it is some impedance which has both resistance and reactance components, then it's a complex quantity. And so if ZL is complex, then your reflection coefficient is complex, right? Now because it's complex, you can plot it in a complex plane. Okay, so you just as you can write a plus ib as a in a plane, right? A point in a plane where you have the x coordinate given as a and the y coordinate given as b. Okay, so real and imaginary part. So similarly, you can define a reflection coefficient plane. So what this is telling you is that the Smith chart is basically a plot of all resistance and reactances that you want to plot, normalized to the characteristic impedance, and then they're plotted in the reflection coefficient plane. Okay, so each point in the reflection coefficient plane, so basically you are uh, define. So if you mark a point on yeah, okay. So if your Z naught is like the characteristic impedance is known, then ZL is, so for different ZL, you have different reflection coefficient, right? So any point on the reflection coefficient plane will correspond to some reflection coefficient value, and that will be associated with some load impedance, some impedance. Okay. Now, why it is required is that you can use to find reactances. So suppose you know the uh, load impedance, and you know the typical dimensions of your circuit, like your transmission line, what is the length and all that, you know that. And then you want to find what is the impedance at the source. So all this kind of calculations can be done graphically using the Smith chart. Now, if you want to design matching network, or have circuits with some specific standing wave ratios, or you want to determine the standing wave ratios, all this kind of calculations can be done with the Smith chart. Okay, and this is extensively used when we talk about uh, having RF or microwave circuits, or designing lossless lines and things like that. Okay. Now, this is how a typical Smith chart looks like. Okay. Now, as you can see here, there is a this line here basically. So you have a just ignore the thing. It should be a straight line. Okay. So what I mean is, if you have a thing like this, so the this line basically, the diametric line here that you have. So this, and then you have some things above and you have some things below, right? So as we know that when we write about impedances, we know that inductive loads are given as something like J omega L, right? While capacitive loads are written as 1 by J omega C. So that's why, like, you can, so this will also come in as we proceed further, but this upper half that you have, so basically this part, right? This upper half is what is called the inductance plane, okay? While the lower half, which is, maybe just this one, is called the capacitance plane, okay? And this line here, the straight line that separates the two, basically, right? Like, so this line that you have here, that is a it's the resistive load. Okay, so it takes real values. Okay, so this is your inductance plane, capacitance plane, and then you have this real line which corresponds to resistive loads only. And now what what can happen basically is that, so we will derive and see how this is coming up. But before that, any circle, so you can see all these circles here, right? So starting from here, you have all these kinds of circles, as you can see, right? So these circles are all constant resistance circles, and we'll see why. Okay. While this arc, so if you look at basically arcs like this, right? So you have many such arcs, as you can see. So all these arcs are basically part of a bigger circle, right? So you can draw a bigger circle. So it's a part of a bigger circle, and those are the X circles. Okay, so the circles that are complete here, as you can see, they are circles of like they are resistance circles, and while these arcs are a part of bigger circles, which are called the X circles. Okay, now we'll see how these equations come up, and then why are we calling them by this name. And then as we move towards, basically as the radius of your circles decrease, the resistances increases. So basically this is your, maximum resistance region, like any circle, like the circle that you have here, like this point here will correspond to like infinite resistance, while the circle which will be here, right? So if you draw a big circle, I'm not drawing the circle, but something like this. So the bigger circle will correspond to the lowest resistance. So if you talk about purely resistive load, this will be like this point here will correspond to your short circuit, while this point here will correspond to your open circuit or infinite resistance. Okay. Now let us see how we get to these equations, right? So why are we saying that these lines correspond to constant resistance circles or constant uh, X circles or reactance circles? Like, why are we defining that? So that will come mathematically now. Okay, so what we can do is, we know that here we are representing normalized impedance, right? So if you have some load ZL, you can normalize it with respect to the characteristic impedance of your transmission line. So in general, like for typical good transmission lines, the characteristic impedances are of the transmission lines are generally real. Okay, if they are very lossy and all that, then it can become you can say like a complex quantity. So now if your R naught corresponds to the characteristic impedance of your transmission line and ZL is your load, then you can define like normalize it given as small ZL, right? And this is how it would look like. So here it would have a real part, small r, and then small x, which is your imaginary part, right? Now we know that this is in the reflection coefficient plane, right? So reflection coefficient is given by this relation here, ZL minus Z naught by ZL plus Z naught, right? Where is my pointer? So ZL minus Z naught by ZL plus Z naught. So you can write it in terms of a real and an imaginary part as well. And you can, so now if you normalize it, right, in terms of the normalized uh, load, then this is how it will look like. So there is a relation that relates the normalized load with the reflection coefficient, which is this relation here, right? This relation. So now here you can again write the reflection coefficient as some magnitude using this relation. So this will be your real part and this will be your imaginary part, right? So now that means if you have some ZL, some load, okay, some load impedance is known, you can actually write it in terms of a real and an imaginary part in the Smith chart. Okay, so if you know ZL or if you know this, you can write it in terms of a real and an imaginary part in the reflection coefficient plane. Now, what you can do is, so you know this expression, right? This is your expression of the real part. Okay, so if you rewrite this, if you start with this equation and if you rewrite this, okay, you get a form like this. An equation of a circle, right, whose center is given as r by 1 plus r and then y coordinate is 0, right? So that means the center of all these circles. So these are, this is an equation of circles. So each value of r will correspond to some circle, right? So each value of r will correspond to a circle where the radius will be given as 1 by 1 plus r, right? And the center of the circle will be given as, right? So all the centers therefore lie on the tau r axis, right? So as you can see here, all these circles, the one that are highlighted in black, right? All these circles, their centers lie on this line, right? Their centers lie on this line. Some network issue happening. I don't know. 1 second, guys. I also need to connect my charger. Once. Sorry, guys. Network condition is very poor. Okay. So, so as you can see here, as you reduce R, which is your, so as you reduce R, that means with um or increase R. So with increasing value of R, your radius decreases, right? So then, sorry, that's what you can see here. So the R circles become progressively smaller as R increases from 0 to infinity. Okay, ending at tau r equal to 1 and tau I. So R is the real part, okay, and I is the imaginary part. So I being 0 and R being 1 point for open circuit, which is this point here, right? So that this point here will correspond to your open circuit, and this point here will correspond to your uh, short circuit. Now, all R circles pass through this point, right? So if you put the value of tau R as 1 and tau I 0, you would see that all of them will be satisfied. So basically, all circles will pass through the open circuit point, as you can see in the figure as well, right? This everything passes through this point, and R equal to 0, R. So if you put R equal to 0, what do you get? It has a unit radius and is centered at the origin, which is the largest. So basically, this point, right? So if you put here R equal to 0, what happens? This term becomes 0 and Y is also 0. So that means the center will be at 0, 0 point, which is the origin, right? This comes directly from this relation, okay? And this will become, so R is 0, so this radius will become 1, right? So basically what you will get is a equation like tau r square plus tau I square equal to 1. So that's a unit radius circle centered at origin. So that is this circle, basically. This biggest circle that you have. I mean this one. This is no longer a circle, but I'll just erase it. So basically this circle, this one. So this is your biggest circle centered at the origin. That's the R equal to 0 circle. Okay. So what did you understand? First is all these circles correspond to a constant R value. Okay. And as we reduce the radius, the R value increases. This is so this point is the open circuit one, this point is the short circuit point, and this biggest radius one corresponds to R equal to 0. Okay, all R circles pass through the open circuit point, which is here. Clear? Okay. Now let us look at this one. The equation do the same, but now for the imaginary part, okay, which is this one. Okay, so for any load impedance, you would have a real part, the resistive part, which will give this relation, and then you have a reactance part, okay, which will have the L and the C contributions, and this will follow this relation. So now again, if we rewrite this, what do we get? We again get a equation of a circle, right? So these circles, as you can see, which are highlighted in, so all these arcs, as we were saying, so these arcs are a part of a bigger circle, right? So all these arcs are a part of a bigger circle, and those circles are the constant X circles. Constant X meaning constant impedance reactance circles. Okay. Now again here, as you can see, the all the centers lie at, so the centers lie at 1 comma 1 plus 1 by x, right? and the radius is given as 1 by x. So again, as you increase x, your radius decreases. So the x circles become progressively smaller as the magnitude of x increases from 0 to infinity. Okay, so ending at again the open circuit point, which is here. Okay, now again here the centers of all the centers of all the x circles lie on the tau r equal to 1 line. Why? Because you can see it from here, right? The x coordinate is always 1. X coordinate of the centers are always 1, and the y coordinate is given as 1 by x, right? So all the centers of the x circles lie on the tau r equal to 1 line. Basically, if you extend this further, right, something like this, right? And if you draw a line, so all of them will pass through this point. So while your x, so the x coordinate of the centers will always be given as, like, will lie on the tau r equal to 1 line. Okay. Now x equal to 0 circle, that's the just the tau r axis, right? Which is like, what does this mean? X equal to 0 means it's a purely resistive load, which is this line basically, right? And all x circles pass through this point, the open circuit point. Okay, so these are the basic characteristics of your constant x circles. Okay, so any point, so if anything lies along this line will be only resistive. Anything above will have some net inductive load, anything below will have some net capacitive load, and that imaginary part will correspond to your reactance for the load. And if you move along this line, the reactance remains constant. So these are called constant X circles. While if you move along a circle like this, right? So something like this, if you move along a circle like this, these are like constant resistance circles. Now, based on whatever we have discussed so far, we can actually try to. So if you are given some mm, impedance, you can try to plot it on the Smith chart. So that's the first thing that we should learn in order to use the Smith chart. So suppose if you are given some impedance which is of the form 1 plus j1. So that means the real part is 1 and the imaginary part is also. So what you have to do, so here in along this line, you have to first see where your along this line where you have 1. So this is your 1 point, right? So if you draw a circle like this circle that you have, that will correspond to resistance like R being 1, right? And then J is also 1. So now what you have to do, you have to look along this arc, right? And see where you have 1. So that is this point, right? So that means now what you can do is anything along this arc, right? Anything along this arc will correspond to uh, the reactance or the imaginary part being 1. Now you have 1 plus j1. So that is your real part is also 1. The imaginary part is also. Wherever they intersect will give you the position of your impedance, right? So which is this point here. So that is your A. So similarly, you can do the same for whatever impedance value is given. So if you have 0.2 plus j 0.2, so what you will do for that, first you look for 0.2 here. Okay, so now you can draw a circle. Again, we know that x like the reactance being 0.2 means it would correspond to this arc, right? Oh no, so this is 2. No, no, 2. So this is this one. So this arc and then this circle. it matches at this point, right? So that is your D. So you can do all this kind of like practice using the Smith chart to represent all these different kinds of like whatever values of impedance you should know how to do. Okay. Now there are two interesting length scales that are involved in the Smith chart. One is wavelength to generator, one is wavelength to load. Okay. So what this tells us is, suppose if we are at some initial, if you are at some initial load, suppose here, okay, and then if you are like, if you want to basically say that this is my load impedance, what will be my impedance at the generator end at a certain distance? So then you have to make use of this scale, okay, the scale that is given here. While if it is the other way around, okay, so if you know the load at the generator and you want to find what is the load at the what is the impedance at the load end, so then you have to use the wavelength towards load uh, scale, okay, and these are written in terms of wavelength, okay. So we'll just like when we do the examples, we'll get an idea about how to use it, okay. Now before we like start using Smith charts for graphically finding out these values, let us remember some points, okay. So first is, if you have any such circuit like this as you have here, so if you have a some circuit where you have some impedance at the generator end, this is the voltage that you get from the generator, and transmission line has some characteristic impedance which is given as Z naught, and then there is a load at the ZL end. Okay, that ZL is your load impedance. So what you can define is, you can define Z as Z equal to L corresponds to the position of the load. Okay, and Z equal to 0 will correspond to your source. Okay. Now another way of defining it is, you can define a quantity D, where D equal to 0 is the, what do I say? Uh, I mean, this point here. So D goes towards this point. Okay. So at the source, Z is 0 and D is L. So D is defined with respect to the load. So D is 0 at the load, D is L at the source, and Z is complementary part of it. So you can define Z as, where do you start? This is the origin, setting the origin. Okay. Now we know that if there is some mismatch between your impedances, then there'll be a reflected wave, right? So at any point, any Z along this transmission line, you can define the potential as V naught plus e to the power minus gamma Z plus V naught minus e to the power gamma Z. So here, what this means is, so you will have a forward moving wave and you will have a reflected wave. Okay. And so now if you want to define the reflection coefficient, that would be the ratio of these two, right? So this is how it would look like. Tau, the reflection coefficient at any particular Z, will be given by this relation here. Okay. So this ratio, amplitudes, you can just take gamma capital L, and then you have e to the power 2 gamma Z. Okay. So based on Z, based on where you are on the transmission line, you would have different values, reflection coefficient. Okay. So now what you can do is, you can now replace, basically rewrite your Z as L minus D. Okay. And gamma, if you remember, the propagation factor that had alpha plus J beta form, right? Where alpha took into account the attenuation and beta was the phase part. Okay. So if you write gamma as alpha plus J beta, and if you replace Z as L minus D, this is how it would look like. Okay. Now this gamma capital L, okay, can be written as something like this. So gamma, the reflection coefficient, will have some magnitude and some phase. Okay, so if you say that at the start, the value is something like gamma L into e to the power j phi L. So if that is your starting uh, value of the reflection coefficient, then if you write it here, as you go, along the transmission line, you would have new phases coming in, and there'll be new contributions also into the amplitude because of your loss, which is taken care by alpha. Okay, so this will be how your reflection coefficient will change as a function of z. Okay, now if you consider alpha as 0, that is if it is not lossless, there is some notification, I don't see. No, it's not opening. Anyways, so if your alpha is 0, that there is no loss. Okay, so then the magnitude of your reflection coefficient, you can, so that's, so this gamma L will be there, and only one phase term will be there, right, which is e to the power j 2 beta d. So d tells you, so if you start from the load, okay, and then d tells you how far you are from the load, right? So so suppose if you know the impedance at the load and you're going away from the load towards the generator side, depending on how far you are from the load, you would have different phase coming in, right? So so gamma L can be written by tau L can be written by this relation here. So this is your expression of your reflection coefficient. Okay. So for any value of d, so it's the same thing. Either you can write it in terms of z or you can write it in terms of d. So at any value of d, which gives you the distance from the load, this is how your reflection coefficient would look like. Okay. So here you can see this tau L already takes into account the initial phase of the reflection coefficient, the magnitude, and any phase, any phase that comes because of the length of the transmission line. Okay, so that is also there. That is already taken into account. Okay, so as a function of d, which is distance from the load, this is how your reflection coefficient will look like. So what this is telling you, that the magnitude will not change, but only there will be a phase change of 2 beta d, right? What is beta? Beta can be written as 2 pi by lambda. So that means it depends on, so as you move away from the load based on the wavelength of the signal, the phases will come d. Okay. Now, if your d is equal to lambda by 2, your phase is 2 pi. So this means that if you move by a lambda by 2 distance, okay, from the load or any point on this, transmission line, basically, we'll get the same point on the reflection coefficient plane. So if you have to represent the reactances in the reflection coefficient plane or in the Smith chart, we would say that if we move by lambda by 2, we get to the same point. Okay. So this is calibrated on the Smith chart, and there comes this scale, which is this wavelength towards generator scale. Okay. Similarly, you can have a calibration with respect to towards the load situation, and then you will have a wavelength towards load scale. So both of them are present in a typical Smith chart. Okay, so magnitude of gamma doesn't change. So you can, so if you, that means if you point a reactance or point an impedance on the Smith chart, okay, and then if you draw a circle, that would correspond to a certain value of impedance, and that would be associated with a certain constant uh, reflection coefficient. Okay, along that circle, the reflection coefficient will be constant. Okay, the phase changes can happen, but the reflection coefficient remains constant. And that constant reflection coefficient will be associated with a constant standing wave ratio. Okay. So these are called the SWR circle. Okay. Now, if alpha is zero, not equal to zero, then what would happen? Then your reflection coefficient will also have a change in the magnitude, right? Because you'll in that case you'll have this 2 minus 2 alpha d e to the power minus 2 alpha d term coming in. So the amplitude will also change. So then it will no longer be a circle, but it will become a spiral, right? But in most cases, transmission lines can be considered to be lossless and then alpha can be set to zero, okay, in practical situations. Now, what we'll also see as we solve our questions. Now, when you draw this SWR circle or when you draw this circle for a particular constant reflection coefficient, it would cut your, um, you know, the tau r plane at 2 points, right? And that can give you the minimum and the maximum resistance that is that this reactance can be associated with, and or this like, so that R max on that transmission line, that can be related to the SWR by this relation. Okay. So what we'll see as we solve is that we can actually derive at the tau R value. So when we point out a reactance, we get a tau R associated with it. So if you know the tau R magnitude, you can actually find the standing wave ratio. You can find the maximum resistance, the minimum resistance, all of that. Okay. And these are the relations which will also be evident as we solve the questions. Now, based on what we have discussed, let us try to answer this question. Okay. So consider the following statements and let us see which of them are correct. So it's a very conceptual question. So here it says that the Smith chart is a graphical indication of the impedance of a transmission and of the corresponding reflection coefficient as one moves along the line. That's true. Right? That's the basic definition. That's true. Now, what it says is lambda distance on the line corresponds to a 720-degree movement on the Smith chart. So what we saw here is a distance of lambda by 2 along the transmission line corresponds to a 2 pi phase. Okay, so 2 pi means 360 degree, right? So that means a distance of lambda would correspond to 720 degree, right? So that is correct. So the second point is also correct. Now, the third point says the admittance chart can be obtained by shifting each and every point on the by 90 degree. Now, if you remember, how do you define admittance? So if you know the reactance, the admittance is the inverse of that, right? 1 by. So, so in terms of the phase, when you do 1 by, it's nothing but a, so basically on the Smith chart, if you are somewhere here, right? And then you say that now, so somewhere here maybe, and then you say that uh, you're going from the, what do I say? The reactance to the admittance form. What do? Admittance is nothing but 1 by reactance, right? So 1 by means it would have a minus sign associated with it. So basically you would have to go this way. So if you are here, you would reach here. So that, as you can see from here as well, that is associated with a 180-degree phase shift, right? Not 90. 90 phase shift will land along on this line. That is not correct, right? So basically any point, if you want to represent it in the admittance uh, plane, then it would have a 180-degree phase associated with it, basically a minus sign, right? And that's a 180-degree phase. So this point is not correct. So the admittance chart can be obtained by shifting each and every point on the impedance chart by 180 degree. Okay. Now next point is counterclockwise movement on the chart corresponds to moving towards the generator. So what it means now? So what we saw is if we at certain z equal to L, some value here, we had some phase. Okay. And as we moved towards the generator, that is from the load towards the generator, what happened? We had this extra e to the power minus 2j beta d coming in. Now, what is this minus 2j beta d telling you? That means your phase. So if you want to plot it in the reflection coefficient plane, if initial phase is phi L, what will happen? You will have a decrease in the phase by 2 beta d, right? So decrease in phase meaning it's a clockwise motion on the chart, right? So that means moving towards the generator, will give you a minus 2j beta d form phase, and that would correspond to clockwise movement on the chart, not counterclockwise, right? If it is counterclockwise, what will happen? New charge, like new phases will be added to it, right? If it was positive, then that would be the case. But you have a minus 2j beta d, so the effective phase term in your reflection coefficient is decreasing. So you are moving clockwise as you move towards the generator. So that means here for this question, only the first two are the correct statements. So this is your answer. Okay. And this is another question which says that when the load impedance is equal to the characteristic impedance of the transmission line, then the reflection coefficient and the standing wave ratio are. So you can understand, if the impedances match, what will happen? There'll be no reflection, right? So when reflection, that means reflection coefficient will be 0. And if reflection coefficient is 0, the standing wave ratio is 1, right? So whenever there is when the load impedance and the characteristic impedance matches, that corresponds to a SWR of 1, okay, and reflection is 0, right? So reflection coefficient SWR is 1. These are very conceptual questions, okay, based on whatever we have discussed so far. So this is like, you can write it in terms of this relation. So basically VSWR is nothing but the voltage standing wave ratio. That's the ratio of maximum voltage to minimum voltage, or maximum current to minimum current. So you can also write it in terms of the reflection coefficient by this relation. Okay. And now if these two values are equal, if your load and the characteristic impedance are equal, you can see from this relation that tau goes to 0. So that means here VSWR becomes 1. Okay. Now, based on this concept, there can be questions like this, where it says that a transmission line is terminated using purely capacitive load given by minus J10 omega. Okay, so this is your impedance. And the VSWR is 1. So VSWR 1 means the load impedance should be equal to the characteristic impedance of the transmission line. So now it says, what is the impedance of transmission line? Okay, so it is a very direct question. So if VSWR is 1, that means there is no deflection. That means the impedance of the transmission line should be equal to this value, which is this, right? The second option, minus J10. Clear? So later we'll see, this is very different. These two things are different. When we talk about maximum power transfer, or when we talk about this, no reflection coefficient, or like this VSWR of 1. Okay, they are slightly different, that we will talk about as we proceed. But for always remember that when there is no reflection, means the react impedances match meaning equal, they're equal to each other. Okay, Z0 should be equal. Okay, now this is another question which says that the impedances Z equal to JX for all X in the range minus infinity to infinity map to the Smith chart as. So we are talking about purely, reactive loads, right? There is no real part here. So it's a purely reactive load. It is saying that, so for purely reactive loads, what all are possible from the Smith chart, right? So it says that a circle of radius 1 with center at 0, 0. So what it means is, so if it is a purely reactive load, that means you can put small r to go to 0. Right? So that means if we go back and look at this expression, okay, so this was our relation of resistive, like constant R circles, right? Now if it is a purely reactive load, that is R is 0. So what happens? If we put R to 0, it's a unit radius circle centered at origin, right? So that's what we have here, right? So it's a unit circle radius with center at 0, 0. So this is the first option matches, right? Clear? You can also solve it like this. So put J equal to Jx. So that means R is equal to 0. So if you put in the equation that we just discussed, you would get this form, which tells us this is how it looks like. So the answer is 1. Okay. So that's how these are very straightforward questions based on how one can use the Smith charts to represent reactances, impedances, and so on. Again, impedance characteristics on a Smith chart repeat after a distance solve. This is a direct question of what we have just discussed, right? We saw that we have this phase of e to the power minus 2j beta d, which tells us that lambda by 2 distance on the line corresponds to a 2 pi phase. 2 pi phase means you get the same value, right? So the impedance characteristics on a Smith chart repeat after a distance of lambda by 2. Okay. Now, when we questions like this, which I have seen in previous years' assignments, so these are again based on like all the concepts that we have already discussed. Okay. So what this is telling you is there is a load at the generator end. You know the voltage that's coming from the source, and then you know the characteristic impedance of your transmission line, which is given in by this blue line here. Okay. And you know the load impedance. Now what it says is if the switch closes at t equal to 0, so when the switch closes, what is the voltage V1 plus? Basically, what is the voltage at the source end, like this end, right? That's what you want to find. So for that, this is a question similar to what we have already discussed in the last class as well. Okay, so what do we do? So here you have 10. So the starting voltage at the source is, so this is 10. Array, this row. So here you have 10, right? And this one is 50. So when you close this circuit, like close the switch, what happens? You know that Z naught, which is the reactance here, right? So that is also equal to 50. So what this means is now when this voltage, there'll be a voltage drop at RG, there'll be a voltage drop along across this point. So if this is 50, this is 50, that means the voltage will get divided, right? So you would have a 5-volt drop because they're equal. So you would have a 5-volt drop at RG, and then you'll have a 5-volt drop across this points. Okay? 5-volt drop across this point, and that is what you are asked to find. So that means V1 plus should be equal to 5. Now, for any such other kind of question where if it was, suppose this was 100, this was 50, then the voltage would have got divided accordingly. It's a typical way of, distributing voltages, right? So based on the ratio of the resistances that are there, the voltage would have got divided. So here, because they're equal, it would be divided into 2. So you would have a 5-volt here. Okay, so that is your voltage at the source end. Now it says that find the reflected current from the load. So what happens? You have a voltage at the source and then it travels to the transmission line. Now Z naught is 50, right? While RL is 25. So that means they're not equal. So there'll be a reflection. Okay. How much will be the reflection? What percentage of the voltage will get reflected will come up from the reflection coefficient. Right? So if we know Z naught and RL, we can find the reflection coefficient by using this relation. You know the load, you know the characteristic impedance, so you know the reflection coefficient. So if you know the reflection coefficient, reflection coefficient is nothing but the ratio of your incident voltage to the reflected voltage, right? So from there you can find the reflected voltage. Now, when you know the reflected voltage, okay, see, this is important. So it is asked that what is the current from load, but it is given as I. Where is my point? So it is given as I1 minus. So basically, you have to find the current at this end, right? At the generator end. So there, you know that the impedance that you have to use, the impedance at this end is Z naught, right? So now you know Z naught and you know the voltage that is getting reflected. So then you can just use V equal to IR and from there find the current, right? That will be your I1 minus. Okay. So how you can do that is, so your initial voltage here is like, this is 5, right? And here, if you take the ratio, what will that be? Z naught minus ZL. So that will be 1/3, right? So that means the voltage that is getting reflected will be given as 5 by 3. That is your reflected voltage, right? And then the impedance at the source end is given as, like the characteristic impedance of your transmission line is given as 50, right? So if you do V equal to IR, it will be, so I is equal to 5 by 3 into 1 by 50, right? So that is 1 by 30, which will give you the value of I1 minus. Okay. Now, once you know the amount of, so something was transmitting, some part got reflected, right? So you know what is the voltage that is reaching the load, right? And that will be nothing but the starting voltage minus the reflected, right? 5 minus 5 by 3. So what it says is find the steady state voltage VL and the current IL at the load. So what will be the steady state voltage at the load? That will be nothing but whatever was incident minus the reflected value, right? 5 minus 5 by 3, right? And now again, if you know the V, so you know V and you know RL, like like the load impedance, you know V. So then you can use V equal to IR to find the current at the load. Okay, so that's how you can solve this question. Okay, so these are very standard questions. Now this we are solving new, like, by calculating it, right? So this kind of calculations or this kind of evaluations can also be done graphically using the Smith chart, and that's what we will do again now. Okay, so let us try to solve some Smith chart problems and see how we can use it. So here it says that the load impedance is provided. Okay, so so the load impedance is provided and the characteristic impedance of the transmission line is known. The length of the transmission line is known. It is said that this 0.1 lambda length line shown has a characteristic impedance of 50 terminated by the load impedance ZL. Now, the first question is locate the normalized load impedance on the Smith chart. This is something we just discussed few slides back, right? So normalized means you have to normalize this with the characteristic impedance of your transmission line. So ZL by Z naught. So this is your value of the normalized load impedance. And now you have to look for, so what you have to do is along this line, see where you have 0.1, right? So you can see this point here. So this circle that you have corresponds to the 0.1 circle, right? And then the imaginary part is 0.5. So now along this line, look for 0.5. So which is here. So this arc, right? So this arc and then this circle, it intersects at this point. So that is your normalized load represented on the Smith chart. Now the question says, what is the impedance at L equal to 0.1? 0.1 lambda. So it's similar to the question that we were initially solving by calculating. It is saying that, so you know the load impedance. It is said that the length of your transmission line is 0.1 lambda. So what is the load at the source? That's what you want to find, right? You're moving towards the generator and you want to find what is the load or effective source impedance at this end. Right? So how to do that? So first what we will do is, once we have located the load impedance, okay, this is the normalized load, you extend this further. Okay, just draw a straight line and extend it further outward. Okay, the point where it intersects on the scale, okay, that would give you a location. Okay, so here the value is 0.074 and the scale is wavelength towards generator. It would be written. So as you can see, wavelength towards generator is written here, right? So now this point corresponds to some location and the value is 0.074. Now it is asked what is the impedance at L equal to 0.1 lambda. So what you have to do, you have to move by a distance of 0.1 lambda starting from this point. Question is, do we move clockwise or counterclockwise? Remember, we just discussed that when you move towards the generator, we move clockwise, right? So then from this point, we will move clockwise by a distance of 0.1 lambda and we will see where we reach, right? Draw a straight line to the center. Okay, so this is a straight line that joins to the center. And here, this you had a ZL value, right? So considering this radius, draw a circle. Okay, wherever this circle intersects this line will be your impedance at the 0.1 lambda distance. So what you're basically doing, you're basically moving clockwise. So you're taking into account the phase change that has happened. Okay, and that is given from the scale here. And when you are drawing this circle, by keeping this radius constant, you are considering that it's a lossless line, okay, in the sense that your um, reflection coefficient is constant. Okay, so as you move along the transmission line, if your reflection coefficient is constant, your this radius corresponds to the reflection coefficient, right? So that would remain constant. So you can draw a circle, and wherever that circle will intersect with this line that you draw from the wavelength towards generator point to the center. So this intersection point will be your impedance, normalized impedance at L equal to 0.1 lambda. So if you're asked to find the impedance, you have to multiply by the characteristic impedance. So you multiply by 50. So this is your answer. I don't know. I don't know why. I just got the notification that you were waiting in the lobby. Trying to get the notification before, but did not manage. So, what we are currently trying to do is we are trying to solve Smith chart problems, basically trying to calculate and evaluate reactances and impedances using the Smith chart. Okay. So I hope you have had a basic idea from also from the course. So I'll just uh, continue with this question. So here what we have done is this was our load. We normalized it with the characteristic impedance of the transmission line. So this was the value. We located that on the Smith chart. Okay. So first we pointed out where we have 0.1 here. Okay. So so this is your 0.1. So you draw a circle. You can draw a circle. Okay. And then you have 0.5. So then you look for the 0.5 arc along this. So all these arcs are there, right? So you look for the 0.5 point. and wherever that arc will intersect with the circle will give you the uh, load. So that is this point here. For the second part of the question, what you have to do, it is said what is the impedance at L equal to zero point 0.1 lambda. Okay, that means you are moving towards the generator. When you move towards the generator, you have to take a clockwise turn. So what you do is, at this is your load, at like at the load end, this is your impedance. So what you do, you draw a straight line from the center and draw a line which extends out. Okay, wherever that intersects with this scale, which is the wavelength towards generator scale, that gives a that corresponds to some length, okay, some distance. So now this point is your load end. From here you move a distance of zero point 0.1 lambda clockwise. Okay, you reach to this point. Now again, if you draw a line towards the center, this is your line, right? And here, when you have found ZL, you can find this distance and then draw a circle corresponding to, like, taking this as your center and this as your radius. So if you draw that circle, anything on this circle will correspond to a constant reflection coefficient value. Okay, so wherever it intersects with the line that you had initially drawn will give you the normalized impedance at zero point 0.1 lambda distance. Okay, so now if you extend this, so what you can do is, so if you want to find the impedance, not the normalized impedance, then just multiply by the load, the characteristic impedance. Okay, so this is your normalized impedance multiplied by 50 will give you the impedance at this distance. Okay. Now, what is the VSWR on the line? Okay, so what is VSWR basically? VSWR corresponds to the ratio of maximum voltage to minimum voltage, right? So you can also write it as maximum of, like, you can equate it to ratio of maximum to minimum resistances that can be present, that can be supported by the transmission line, right? So now for the Smith chart, we know that as the radius decreases, the radius of these circles, all these circles that you have, as the radius decreases, the resistance increases, right? So any point here would correspond to larger resistances, while the points here will correspond to minimum, the smaller resistances, right? So that means now if this is your tau r equal to constant line, okay, so you're drawing a circle, wherever that circle will intersect with this diameter basically. Okay, so the tau r equal to one line, basically the real resistive line, wherever it intersects with that point, that corresponds to the maximum resistance that can be present, right? And that is your value of VSWR. Okay. It's like, what is the reflection coefficient? So this is very straightforward if you understand what this actually means. So any point on the Smith chart corresponds to a reflection coefficient value, right? So from this point, this radius is nothing but the reflection coefficient. Okay, the magnitude of, like, this length corresponds to the magnitude of the reflection coefficient. Okay, so what we'll do is, you can use a protector or you can use a scale, whatever, measure like this distance, put it on the scale that you have here, and that would give you the value of the reflection coefficient. Okay, if you want to find the phase, okay, so because in the transmission line, if it is lossless, we know that the reflection coefficient will remain constant while the phase will change, right? So if you want to find the phase at this point, what you will do, you'll, so this straight line that you have drawn from the center, right, it will cut at this. So this angle here talks about the argument of your reflection coefficient, right? So wherever this point will cut, that will give you the value of the phase of the reflection coefficient at this point. Okay, now if you want to find the value of reflection coefficient at the other distance, what you do, so you can understand magnitude will change. And so again, this line, when you have extended it outward, here this scale will give you the argument, the angle, right? So that means at this point, the ZL point, like at the load end, your reflection coefficient was so for this question was 0.855, and the angle or the phase part was 126.5 degree. While here at the end, that is like zero point 0.1 lambda distance away, there again the magnitude remains the same, but now the phase is 55 degree, right? So that's how you can use the Smith charts to calculate this kind of like solve for this kind of problems. Okay, so there can be similar problems like here. So here what is given is your ZL is given, okay, and Z naught is 1. So that means you don't have to externally normalize it anymore. Okay, so the characteristic impedance is already 1. And then it said that your length of your transmission line is given as 0.25 lambda. Now you have to find what is Z at this end, at the generator end, right? That's what you have to find. So it's same as what we have done in the last question. So what you have to do is first you have to locate the load on the Smith chart. How do you locate it? Look for the circles with zero point 0.2 and the arcs with zero point 0.2. Okay. So as you can see here, so if you go along this line, this corresponds to zero point 0.2. So there will be a circle which would correspond to zero point 0.2. Okay. And then you have to look along this line to find this arcs, all these arcs that you have, right? And look for zero point 0.2. So again, there you'd see that there will be a zero point 0.2 here. So if you extend that further, right, that is your load. This is your position of the load. Now for this, what you have to do now, you want to move by a distance of 0.25 lambda. So first let us locate the position of the load in the wavelength towards generator scale. Okay, so what we'll do, we'll draw a straight line passing from the center to outwards and see where it will cut this scale, right? So that distance is given as 0.467 on the wavelength towards generator scale. Now you have to move clockwise because you're moving towards generator by a 0.25 lambda distance. So let us move by a 0.25 lambda distance. You end up reaching here, right? Draw a straight line back to the center. Okay. So this is the straight line that you would get. Okay. Now what you do from the center, if you take this distance as your radius, okay, and with the center here draw an arc, draw a circle. This circle will intersect this line at this point, right? So that is your value of your um, load at a 0.25 distance from the load. Okay. So that's the impedance at the source end, basically. Okay. So that is what you get here. Clear? Now, again, if you have to find VSWR, what you do? See where this circle, okay, where it intersects on the, so it would intersect at 2 points, right? So if you draw a circle with this radius, it would intersect at 2 points on the resistance line, right? Now this point would correspond to a larger resistance, while this would correspond to a smaller value. So this is this is the largest value of resistance that you can get, and this is the smallest value of resistance that you can get, right? For this respective value of reflection coefficient. Okay, so that means now this is your Z max, and that's the VSWR. Okay, while this point here correspond to the Z mean. So if you're asked what is the like uh, the minimum impedance that can be supported in the line, then this is your value. Okay. Now, how far from the load is the first voltage minimum? So for this question, so you can understand. So it is said that, so basically you are at the load. Now you are moving towards the generator. It is said that how far from the load will you have a voltage minimum? So when will the voltage be minimum? So voltage minimum would correspond to a minimum load, right? Because if load is more, then the drop of voltage will be more, right? So you want to find the location of minimum impedance. Okay. So voltage minimum means look for the position of minimum Z that can be supported. So that is this point, right? Now, how far? The question is how far. So what you have to do? So from this point, if you extend and look at the length towards generator scale, this is 0 here, right? Okay. So basically this distance, okay, so your initial load location, this is the location of your minimum Z. So this distance between the two will give you the value of the distance that is required to have the first voltage minimum. Okay. Okay. So now if you are asked current minimum, then you have to do the opposite. Minimum means maximum load, right? So then you have to look for this point, the Z max position. Okay. So all these different kinds of questions can come up. So in many questions, what can happen is like, see, in when we talk about the scale, the wavelength towards generator or wavelength towards load scale, we are writing it in terms of the wavelength of the signal, right? So in some questions, what can happen is the length initially can be provided in standard units. Okay, so then you have to be careful about using the signal frequency. So suppose here it is said that you have this air-filled two-wire line with some characteristic impedance operating at certain frequency, like 3 gigahertz. Okay. So now because your is at 3 gigahertz, you can basically use this relation. Okay. This is speed of light and this is f, which is the frequency. So from here, you can actually find the wavelength of your signal. Now, once you know the wavelength of your signal, you can change this length that is provided to wavelength units, right? So this will again be 0.25 lambda, right? Basically, how much, like writing this as a in comparison to the wavelength. So be careful about this information that would be provided in the question. Okay. So now the question becomes similar. So you know the load, okay, you know the characteristic impedance that is Z naught, and you know what is the distance in terms of wavelength, that is again 0.25 lambda. Okay, so it's a similar question again to what we have initially solved, right? So first normalize it with respect to Z naught, then locate it on the Smith chart. Okay, so if you locate it, you have to look for 0.2 on this line and 8 along this arcs, and then look for where they intersect. This is your position of your load. Okay, you have to extend it further, see where it cuts the wavelength towards generator scale. Okay, and then go clockwise by a 0.25 lambda distance. It reaches here. Okay, if you draw a circle with this radius, okay, see where that circle intersects this line, and that will be your load at this distance. Okay, so that's how you can find. Now if you want to find VSWR, again look for the maximum resistance point. Okay, so these are like typical standard questions, just you have to use it for a few times. Okay, now there can also be questions where it's other way around, where the impedance at the source end is given. You have to find the impedance at the load side. Okay, so then the process is similar, but we will use another scale. So in the Smith chart, there'll be two scales provided. Okay, so one is wavelength towards generator, which we had been using. Another is the wavelength towards load. Okay, so you'd see here it's written. So wavelength towards load, and then you have wavelength towards generator. So when in questions where you know the impedance on the generator side, you want to find the impedance on the load side, then you have to use the wavelength towards load scale. Okay. And another thing is because you're moving towards load, you have to rotate counterclockwise. When you go towards the source, you're going, or towards the generator, you're going clockwise. Here you have to go counterclockwise, right? That's the difference. So here it says, you know the Z, the normalized impedance at the source. You know the length of your characteristic wire. You need to find the load impedance. What do? So first you locate this source impedance. Okay. So again, this is a typical thing. So you lose. So here, what would happen is it would directly lie on this point because it's a purely reactive load, right? So this is your position of the source impedance. Okay. Now extend it further. Here you have to look at wavelength towards load scale. Okay. So if you look at the wavelength towards load scale, the value is given as 0.189 in this scale. So be careful about using this scale. So now you cannot go clockwise. You have to go counterclockwise so that you go towards the load. Okay. So go by a distance counterclockwise towards the load. You end up here. Okay. So now again draw a line inwards. Okay. So this point here, basically now if you draw that this, you don't have to draw new circles here because it's already on the reactive, like it's purely reactive load. Okay. There is no resistive part here. So that means wherever it would intersect at this point will give you the value of the load at the, like value of the impedance at the load end. Okay, so that is your value, for the first part of the question. Okay, now if it is asked what is the distance from the load to the first voltage minimum. Okay, so first voltage minimum corresponds to the minimum value of resistance, right? So that means you need to find this distance, right? And that is straightforward because this corresponds to zero value. And if you know how much is this distance, this is given as 0.064 on the wavelength towards load scale. So that means if this is 0, this is 0.064 lambda, that means that's the distance, right? So that's your answer. Okay, so this is your zero line. Okay, and there you have your minimum voltage point. Just look at how different they are on this on the wavelength towards load scale. Okay, the difference in the distance. That's the answer. Now, next part is what length of the open circuit line could be used to replace ZL? What it means is now you know what is your value of ZL, right? But can you replace this ZL by a certain length of a open circuit line? Okay. If you want to do that, what will be the length of your open circuit line? That's the question, right? So for this, what you have to do from the position of ZL, okay, we want to move towards a new load. Okay, that is towards the end of the open circuit line, which is this point, right? We want to move along this point. Okay, so basically you need to find, you are here, you want to go here. Okay, so how much should be the length, right? So this occurs at 0.25 lambda on the wavelength towards load scale. What you do, basically you are extending it further. Okay, and then, so if this is your, in the wavelength towards scale, if you know this point, okay, and you know the position of this point, so you just like do a subtraction, right? So you start from 0 here, you know the position of this point, that is 0.25, and you know the position for ZL, which is 0.064. So 0.25 minus 0.064 lambda will be this distance, right? So that should be the length of your open circuit line, which can be used to replace this ZL. Okay, so that's how you can address this kinds of questions. Okay, now as we discussed, like the Smith charts, one of the major applications of Smith charts is to have or like design impedance matched circuits. Now why impedance matching is so important is that if you have proper matching of impedances, you can achieve maximum power transfer. Okay, so there are two things. So there can be two ways. Okay, so roughly speaking, so basically one is the impedance at the source end. Now you can choose the load, you can adjust the load such that it is matched. Okay, or what you can do is you can keep your load constant and vary and see what happens if you change the resistance or impedance at the generator side. Right, these are the two things you can change. So for the first case, when you want to So you can solve for this question. So what you can do is you can actually draw a circuit with some RL, C, okay, and then divide the resistances, find the power, value of power, and impedance, okay, derivative of power with respect to impedance, like fix it to zero, and then take del square P del R square, okay, and then set it that for a certain ZG, which is your impedance at the generator, if your load is a complex conjugate of the impedance, okay, this some network again, this network, yeah, I think it's fine. Okay, now that you have to adjust the load. Remember that maximum load does not mean that all the load is being delivered, okay? It's the maximum load delivered, and that's actually half of what you have at the source, okay? So that's one way. Another thing is you can keep your load constant, like fixed, and then see what you can do with ZG, with the source impedance. So in that case, if you do the same thing, so if you put like ZG as a complex conjugate of ZL, what would happen is the initial voltage would get divided between the two. Okay, so that's a way, but that will not give you the maximum power. When can you have maximum power? If you put the source impedance to go to zero. Okay, so when you have a certain load for an ideal source, what we need or what we want is the source impedance is minimum. Okay, zero. So there, the maximum, all the power generated here would come to the load. Okay, but if your source impedance is fixed and you want to just vary the load and do an impedance match, there the best you can do is you can set your load impedance to be the complex conjugate of your source impedance. Okay, so that's the condition for maximum power transfer. Okay, so it's important to note that when we talk about, so this was one of the questions last time when we were discussing, like these questions have come up where there are two situations. So one is the case of no reflection, okay, or when the VSWR is 1. That's the case where your characteristic impedance of the line should be equal to your load impedance. Okay, so if you have 1 plus j at the load, your characteristic impedance is also 1 plus j. That's the condition for no reflection or VSWR being 1. But when you are talking about maximum power transfer, okay, so there, if your source impedance is 1 plus j, then for maximum power transfer, your load should be 1 minus j. Okay, the two different things. Okay, now, so that means you can understand that impedance matching is important and you can achieve that by,
Madam, one thing.
yes,
In first case, like maximum power transfer theorem, we don't bother about Z naught, madam.
we
Z
don't
naught,
bother about Z
Z
naught.
naught, Z naught will not come into picture.
No, no, Z. So here the one way, no, it can come in the picture, but the main point is that, so then you have to do, so that's the thing that I was just coming to that. So basically, when you are talking about matching circuits, you have to do a matching on both sides, basically the source side and the load side. I mean,
Okay.
first you have to do a match at the source end where your ZG or the source impedance, whatever at the generator end, that should match with the characteristic impedance of your um, line. Okay,
Okay.
and then again at the load end it should match with ZL. So that's the what do I say? That is required for the maximum transfer to happen.
So no minimum reflections are there. So ideal, like good transmission line.
So that's a good transmission line. There'll
Okay.
be no reflection that is there. So but the difference that I was trying to point out is that the condition for maximum power transfer and the condition for no reflection are slightly different when we are looking at I mean, you
Yeah,
understand, right? So
yeah, understand. But the thing is, impedance. We are discussing impedance matching. So
mm,
impedance matching means Z naught is equal to ZL, as per my knowledge.
so
So it,
impedance matching. So when you do Z not equal to ZL, there'll be no reflection. Transmission will be
uh,
better, and that's the condition for proper transmission. That is correct. Okay,
that is correct. But
but
in case of
uh,
Z, when we are talking ZG and ZL complex conjugate matching, then
mm,
we are neglecting that Z naught. There is no talk about Z naught. So we don't consider Z naught, or every line is having its own Z naught, right?
yes, that will like for a practical purpose, you will always have some like real. Generally, for a good transmission line, it's a real quantity, but it is always there. So you would have a
Okay.
net Z not being there, and for so suppose you have matched ZL and Z G. Okay, so suppose this condition is satisfied, but your Z naught is very different and the Z
Okay.
naught do not match. So then it will be a problem because then there'll be a lot of reflection that will come in the
Okay.
picture.
Okay. 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 Thank you.
Yeah, welcome. And
Continue.
in this, yeah, thank you. And so this kind of matching can become even more important when we are talking about cases where the impedance is very much sensitive to frequency. So suppose when you're talking about antennas and things like that, okay, so many antennas would have a so the impedance would vary a lot as a function of frequency. Okay, so because they can have very selective band of frequencies that they work on. So for those kind of cases, it's very important that we have this impedance matched networks both at the source and the load so that there is proper transmission. Okay, so that is very important. Okay, so you have to do one matching at the source end where your ZG should match with the Z naught of the transmission line that is at the source end, and then again your ZL should match with the characteristic impedance of your transmission line. So you have to choose the transmission line accordingly, or you have to change your impedance accordingly and do all those kind of changes. Now, how can you do that? So there can be various ways. Okay, so uh, one of the ways would be to do some transformer matching. Basically, you do some changes such that the voltages are adjusted in such a way that the reflections are countered and you can have a matching situation. Okay, or you can have lumped element matching where you what you do basically is you add certain lumped circuits here so as to make the effective load to get matched, like add something in series, something in parallel, and make a circuit where it gets matched with your maybe characteristic impedance of your transmission line. So you can do that. Or you can have there's another way where you have this quarter wave transformer. So this is similar to the question that was initially discussed in the last class, where there were this multiple lambda by 4 transmission lines where the source for one was acting as the load for the other. If you remember, they're like cascaded uh, the few problems like that we had solved. So what it means is you can add such quarter wave transformers to change the input, adjust the input impedance or the load impedance in such a way that they get matched in your required zone. Okay, so for this was the relation. So in each such sections, if you know the ZL, if you know the Z naught, you can choose your input impedance accordingly. So if you want a certain input impedance, what you can do is you can use another combination of Z naught and ZL at that end to get a certain Z in. So all this kind of combinations can be done. But as you can understand, this is a quarter wave plate means this is very much wavelength dependent. So in questions where your signal has a range of associated with it, or you're talking about like a if the wavelength varies, in those cases it would be difficult, right? Because it's very much wavelength dependent. So there you have to look for other ways which are less sensitive to wavelength. Okay. Now another could be this stub matching network. So there can be different ways of doing it, but the most standard way is this or the one that we're discussing now is this single stub matching network. So basically here what you want to do is you want to add a stub, okay? And that is something which you will add at a certain location from the load. Suppose you have a load, okay, and you want to tweak the load in such a way, okay, do some add something in parallel to it so that the load gets matched. So for this, what you add is called the stub, okay, and that's nothing but a resistance, or like not resistance, like some impedance that you add in parallel, okay, to the load. So there are two things. First is what should be the length of your stub, okay, so what are you adding, and at how far are you adding that, okay, from the load, okay. So for this kind of things, and if you want to solve it using the Smith chart, what we do basically is we go to the admittance uh, chart, okay, because we are adding something in parallel, so it's easier to uh, do this calculations if we go to the admittance chart where we just, so your z naught becomes minus y naught, okay, because you are going a 180-degree pi, like 180-degree phase shift. And similarly, if you know the ZL, which is your initial load, you can write it as YL in the admittance chart. Okay. So that means for a typical Smith chart, you have to go 180-degree phase shifted. Okay. For going from, you know, the typical impedance chart to the admittance chart. So now what it is told is if you know YL, you know Y naught, which is corresponding to the characteristic impedance of your, or characteristic admittance of your transmission line. Okay. Now the question is how far from this ZL, okay, how far on the transmission line will you add your stub? So for this, what we will do is basically we want to go to a location where your new admittance takes up a form of 1 plus G. It's a it's a way of calculation. Okay, it's nothing but you are trying to calculate it in such a way that simplifies your uh, question. The main question is to match the impedance. Okay. So what you do is basically if this is your load. So for a Smith chart, you know, you locate this point and now you draw a circle just as you were doing for the last cases. Okay. So draw a circle and then you want to see where it intersects with the unit circle. Unit circle means where your resistance or the real part is 1. Okay. Wherever it will match or it will intersect the unit circle, there your admittance will take a form of 1 plus JB, right? So now at this distance, at a distance L, which you can again find from the scale in the Smith chart, your new impedance has taken a form of 1 plus JB. The same YL has now taken a form of YL prime. Okay. So this is the length where you want to add your stub. Okay. So if your question says where are we adding it, what do? We first locate YL on the Smith chart in the admittance chart. Okay. And then we see where this circle intersects with the unit circle where the resistance is 1, such that the new admittance takes up a form of 1 plus JB. Okay. Some B value you will get from the chart. Okay. And this length is that the difference between these 2 points on the scale in the Smith chart will give you the length where you have to add your stub. Now, because you want to match the impedance, what you basically want is once you have added the stub, so here you have to add the stub. So you know how much from the load you are adding the stub. But now, what should be the length of the stub? How do we find that? So whatever we add here, basically you are adding something in parallel here, right? Adding something in parallel here. Now, this the admittance for this stub plus this value that you have got, the new admittance, right? That should be equal to 1 plus J0, because if that is the case, then basically you have matched it because the effective value of the impedance has gone to 0, because 1 and 1 this side it will get cancelled, right? So that will already tell you that your stub length should be given as minus JB, right? So whenever you have found right, the distance will give you this length, okay? While minus JB, that should be, so this B that you see here, right? That will give you the length of your stub. Okay, so
So
in this
our
kind of,
aim is to
yeah.
nullify the reactance part, right, madam? When we nullify
So
the reactance part, only the resistive
so
part will be.
basically the whenever you are adding this length,
Mm,
sorry. So initially when you are adding this length, right? This was your load. Now
okay.
you have moved from the load to this point and then you have added your stub, right? Now at this point you have
Mm.
already set your like your resistance part, like the real part has become 1,
1
right?
plus JP. Okay, okay. Yeah.
So this is 1 plus JB
Mm,
at this distance. Now you
mm.
add something to it such that this form becomes 1 plus J0. What will happen? That means this is already
Real.
matched, right?
Yes,
One
yes.
real
Only
part is
real
already
part.
matched.
Yes, yes, yes.
That is matched, and this becomes 0 if you
Mm.
add that stuff. So then it ultimately it's matched.
Yes, yes. Got it.
Okay, so yeah, so that's how you can. So this is how you can, like, these are the steps basically. Like for a Smith chart problem, this is the step that you have to follow in order to find this length of the stub or where you are adding the stub, all this kind of questions from the Smith chart. Okay, so yeah, that is it. Is if there is any question, you can ask me.
Yeah. As of now, no more questions, madam.
Okay.
Actually, I already am teaching this electromagnetics and transmission lines in my college. So I want to
Okay.
improve my knowledge in that. That's why I have registered for this course.
Oh,
Almost
thank you.
uh, almost for all 100% assignments, I got the score. But
Okay.
one or two I missed. Only 91 question I got wrong. Later I
Oh,
realized that I myself did that mistake. Uh, uh,
yeah.
Assignment 3 and 4 solutions I could not find in the portal, madam. If possible, can you arrange that 3 and
There's
4
a so I think there's a Excel sheet that is being shared. So I
Okay.
hope it is shared. So where all the videos like this thing is getting recorded, right? So we
Yes.
upload the
Uh,
video and we also upload the PDF that I'm like discussing. So
okay. Okay. Yeah.
there, so
Uh,
I think maybe that link, if you go to that link for
mm,
the third and the fourth week, so there
mm.
you'll get some in most cases we don't always solve all the questions that are there in the assignment, but
Okay.
similar questions or similar kind of things, so that you can get. So I think that link you have, or like there are YouTube video links will also be there,
Yes,
and there'll be a link to a
yes, madam. I found. I have found. I have seen that. Seen those links and YouTube links, everything. Mm.
so I think there, even then, if there's some particular question, you can tell me. I can try to solve and like get back to you.
Okay.
Or otherwise, like you can just maybe refer to the third or fourth week
Okay.
like
Okay.
classes.
Those corresponding videos I'll go through it. And William Haith only you are following, madam. This
I am
Smith.
basically Smith
What?
chart. I actually did not follow any books as per se. So what I did is there in for this course. Then
Okay.
I looked at internet, like there were many problems that were solved. So when the problems that I were seeing is I got it from the internet, like there are different PDFs from different universities where they
Okay.
have solved different such Smith chart problems. So I just took up some questions from there and discussed. So it's
Actually,
like
I
not.
could see a good collection of problems on Smith chart in today's class. So that's why I'm asking the reference.
Yes,
Uh,
yes. I think this is from some university. I don't remember. Basically, I looked through the internet to see what are the
okay.
different speed chart problems. So
Okay.
different universities sometimes have this, they have their own,
Mm. Course
assignment
files.
problems or
Yes.
course, so that those which are made online. So
Mm.
from there, I just figured out some
Okay.
examples.
Okay. Thank you. Thank you so much.
Yeah, yeah, yeah. Thank you. Thank you. Thank you.
Yeah.
I'll just end the meeting. Okay.
Sure, madam. Good night.
Good night.